is in the physics department at the University of Toronto, a Canadian chair, research chair in theory of quantum materials, and a fellow of the Canadian Institute for Advanced Research in Quantum Materials. He is a theoretical physicist who specializes in condensed matter physics of complex quantum materials, including quantum spin liquids, topological phases, high temperature superconductors, and frustrated magnets. So without further ado, introduction to correlated quantum materials. Thank you.
Thank you. Good. Yeah, so thanks for the nice introduction, and thanks for the organizer for bringing us together. This is really amazing, like how undergraduate students, how far they can reach. Yeah, so it's a real pleasure to be here and just discuss about some part of my research. So I'm going to say, just I put an introduction to correlate quantum material because given a 40-minute or 35-minute, I don't think I can explore all of what I'm doing, but I'd like to get you where we come from and how we go there, and some excitement that I'd like to share with you. Okay. So here's my first question. Of course, what is the most remarkable discovery in human history? Of course, this is a subjective question. Some might say, well, fire. Yes, that's true. Some might say plastic. Some might say, well, silicon. And so on. And I think it's a bronze. So to me, it's a discovery of bronze that, in fact, have allowed humans to become, putting together, have all that agricultures and so on that actually started from a bronze. If you go back to the bronze, in fact, it's a 90% copper and 10% of this tin alloy. And how that happens was probably by an accident. And do you know how to make a bronze? In fact, all you have to do, collect the particular color of the stone and you melt it. And that's what our ancestor has done that 4,000 years ago, or even longer, 6,000 years ago. So if you go back to the human history, in fact, that we classify or categorize our ages by the name of materials. Of course, that doesn't mean that our cultures are just tied to the material, but of course, there are other things that are with us. But in fact, the material has allowed us to become a human of modern age. So if you go back to the Stone Age, which has lasted, like you can see there, like millions of years. In fact, the bronze is the one that get out of this Stone Age. And as I said, we were able to get some culture since then. And after that, we know it's an Iron Age. And then after that, modern revolution was allowed because we had a silicon. Okay, so silicon is a semiconductor, as most of you know. And how we make a silicon, where we got them? Well, now instead of stone, you melt the sand. So sand is made out of silicon oxide. And if you put it on a fire or put it in a hot temperature, the oxide will go away. And then we get a pure silicon. And that silicon with a p-doped, n-doped, some of those tuning, in fact, is a building block of the transistor. So discovery of transistor is in fact that, has allowed us to have a modern revolution. But without the silicon, in fact, that would not have been possible. Okay, so what's the next? Yeah, we got a silicon age. And then what's our next revolution? Again, this is again subjective question, but I'll put it a quantum age. So that's where I believe that we are moving on. And I'm just gonna borrow the picture from this is a Google it's a quantum computer. And if you look at these details, in fact, that this is based on the aluminum. So here, aluminum is a superconductor, and the critical temperature where below which it becomes a superconductor is only 1 Kelvin. That is, in fact, colder than the outer space. So you go outside, and then outer space is even, higher temperature than the going inside this quantum computer. So the question is then, we have this periodic table of elements. These are what we can find on our Earth. And here is our famous bronze guy, copper. And during that time, we had a silver and gold. And if you go back to your, those kingdoms, and they had this famous, this fancy gold and those things are discovery of, actually tied to the discovery of these coppers. And here is our famous silicons. And one can dope with the fluorine here and phosphorus here, and the aluminum is also here. So some of those materials are the one that we are using them. But the next question is then what will be a building block? What will be a next material that will generate us or give us to allow or having a hardware for the quantum computers? Okay, so there we are going. Okay, so to understand that, we probably like to go back and thinking about, okay, where the physics comes from and what does that mean? In fact, the 20th century's reduction or reductionism was very popular. In other words, we are trying to find the elementary particles, like what are these things that are made, like even us, or chairs and desks, and they are all probably made out of some elementary particles. And we were very successful to find it out, those elementary particles are made out like, you find the quarks and the leptons and force carriers and W bosons and so on and so forth. But all of those elementary particles are classified into two categories. One is the fermion and the other is the bosons. And so these are based on their statistics. You can see that leptons and all of those will belong to either fermion or bosons. Okay, so then one can ask, okay, I showed you that aluminum is a superconductor, copper is a metal actually, and silicon is a semiconductor. The difference between them, if you're just looking into the atomic tables, then they have more electrons or more nuclears, heavier ones. So backing into the elementary particles, we probably won't be able to understand why some are metal, some are semiconductor, even some are magnets, where you can use the magnets to, guide the directions, or magnets in your phones allow you to hear the voice, get some sound and things like that. So we need to go a little beyond thinking about those elementary particles. When you put them together, like billions and millions of those, we are actually getting something different, and they cannot be understood based on the elementary ingredient. Okay, so those are so-called, I'll call it quantum emergence. We are dealing with the many particles, and they are all kind of interacting. And theory of everything is just this Schrödinger equation. It's in fact, you can solve this Schrödinger equation with the Hamiltonian. And if I know what is the evolution of the wave function, we may be able to solve everything. But the problem is that we are dealing with number of particles that we are dealing with is actually, if you have a 1 millimeter grain of salt, the number of atoms inside that 1 millimeter is the 16 quintillion atoms. So this is impossible to solve it. Then we need an innovative idea to understand what's going on. So here is the second question that I want to address is that why some are metal, some are insulator. In addition to that, second question that I'm going to share with you is that do we get new emergent quantum particle that are different from boson and fermion? We know that in nature that we have found so far, all of them falling into one of two. Can you get something else, materials? So that's what I like to discuss, present. And here's my outline. I compose into three pieces. First is a quantum material with a standard theory, which you can learn, and you will actually learn in some undergraduate or graduate studies. And second is the standard theory 2. And the first two will tell us why some are metal, some are insulator, why some are magnets, and some are non-magnets. But that is not possible. I mean, that is not going to tell us the third ones, which is basically beyond the standard theory. That my second question tied to it is can you get a new emergent particle different from elementary particle that exists in nature? Okay, so let's begin with the first quantum materials of the standard theory 1. All right, so let's begin with the hydrogen atoms, and some of you are probably very familiar with it. There is a particle wave duality. I can use electron as a particle, but I can also write them as a wave function. And wave function of psi here, one is referring to single particle. I have just one particle with a position of R, and that are governed by the Schrödinger equation. So instead of F equal ma, we are going to use this Schrödinger equation to understand the wave functions and how the wave function change in a time. And taking a square of those wave functions tell us the probability of finding a particles and so on. So in some situations, what we are dealing with most often is that the Hamiltonian has a time independent, but it has a space and the momentum. And if that's the situation, then this Schrödinger equation can be reduced to an eigenvalue problem. That's why you are learning matrix diagonalizations and so on in your mathematical math courses. That's required for the physics, because it's very useful to know the physical properties. So examples of Hamiltonian in the hydrogen atoms, you have kinetic energy, and then you have potential energy, and that potential energy is nothing but the Coulomb interaction. And then we can solve this differential equation or eigenvalue problems, and we end up with the energy levels. There are low energy levels, and there are high energy levels, and so on. And then I need to classify those energy levels, and they comes with the so-called principal quantum number, like n equal 1, n equal 2, n equal 3. So we put them underneath the interaction, underneath this energy here, as well as wave function, to classify the state. We are not following a particle. We wanted to classify the state, the quantum state that electrons are able to take it. Okay, so like we want to identify the chairs and the desk, and then after that, we'll put the electrons. So that's the pictures of the quantum mechanics or quantum physics that begin with. Okay, a simpler example is a 1D, artificial atoms. So we like that. And only things that we have is the potential is, let's say, attractive, because Coulomb interaction is attractive. And then we solve this problem, and you probably have seen a cosine function or sine functions. That's your energy, that's your wave functions. And here again, energy levels are going to be classified by the quantum number, n equal 1, 2, 3. And you see that the probability of finding particle is a square, and there is a probability that goes outside the box of the potential, and that we call quantum tunneling. So that's what we know about the atom. So how do we go from here to a solid, okay, where we have like a quintillions atoms? Okay, so one way to do it is the following. I have one atom, okay, I said this, and I have energy levels, so 1, 2, 3, those are principal quantum numbers. I put the two particles, two hydrogen atoms, but they are infinitely far away. So that's the situation. I have two independent atoms, then these are infinitely far. In that case, my energy levels will be two degenerate state. I have two of the particles, and each of them will have this two lowest energy state, and then you have other ones and so on. So this to build up, just to make a copy of the two hydrogen atoms. But what happens if I put them together? If I get them very infinitely far, and then they get closer and closer and closer, my wave function has to change. And that's because they can tunnel each other. Electrons can tunnel each other, and that'll give us the molecule. So diatomic molecules such as hydrogen 2 will have these functions. I got them close. You can see that there is now tunneling appears between the two, and that tunneling is going to mix the two degenerate state down here, and that two degenerate state will evolve into these pictures here. And one of them is called bonding, and the other is called anti-bonding. Okay, and the separation between the two will be proportional to how much you can tunnel each other, how far close, what are the distance. Of course, that's optimized because you have a kinetic energy, not only just the potential energy. All right, so now we want to move to the solid. Solid is a periodic array of those potentials. Okay, so let's begin with it. I have atomic distance of the D, which is called atomic, it's atomic distance, and they have like a size of angstrom. Imagine that I have L atoms, that's a number of atoms, and that means the size of the length of my system is going to be L times the D. And if that's the case, when each atom is infinitely far away, just think of a molecule. I have infinity L of them instead of 2. Well, I know how to solve this problem because L of them are independent. So I have L degenerate atoms at this one here, and then n equal 2, n equal 3, and so on and so forth. But again, I get them close by because solid make that solid because they are close by and they are very rigid. So in that situations, this is what's going to happen. So when atoms get close, there will be a tunneling to each of them. And this L degenerate number of the state, which are provided by the number of the atoms. So we don't change the degree of freedom. Degree of freedom is preserved, and that forms the so-called Hilbert space. But in any case, so here is L degenerate state, which will form this mixing them each other, and there will be an L state here. Okay. All right, so this size of the width, that's the size of this energy distance is called bandwidth. That's where the solid comes in. Okay, so periodic pattern in a real space, let's think about that. Once you have a periodic pattern in a real space, we use a Fourier transform. So that's why we learn Fourier transform, at least from a physics point of view, that Fourier transform in a space is when you have a periodic pattern in a space. If I have a periodic pattern in a time, then I'll do the Fourier transform in a frequencies, right? So this has a periodic patterns. That means there is a wave vector associated with these patterns. So that means when this potential goes to zero, I know how to solve the problem because it's a free particle problem, right? So we have plane wave, which you probably have heard of, at least to solve it. But I have these periodic patterns. So that means this is example of my wave function in solid. So this one here, that lines go like this. This is a real component of my plane wave. So this is a cosine function. In addition to that, I have this periodic potential, which reflect that my wave function of this part, which we call the U, or so-called sometimes we call Wannier function. That's going to be periodic because it has to reflect the periodicities of my solid. So wave function will have now two quantum numbers, not just the principal quantum number. I'll have the so-called K, which is coming from periodicities of my solid. Okay, and that is called wave vector, or just called the momentum once in a while, because you multiply Planck constant, it'll be some momentum. All right, so I have two quantum numbers. So recall that we had this L degenerate state, it's energy levels, but each of those states will take a unique value of the momentum or wave vector. So I can plot it in this way. It's a function of my wave vectors. Each of those L state will take some value of the K. So you can see that all of those will have L state. Okay, and then n equal 2 here will go up here. I just plot out all of those available states. These are number of chairs that we have identified. Number of chairs we identify depends on the background, and that background is my solid, pattern of the solid. So again, here is my bandwidth, and you note that there is, and then we use this n to be a band index 1, and there is this forbidden state, band gap. So any particle that comes in, doesn't matter, there's no one can take this particular energy state. There's no one can do that. In other words, there's some river here, and then there's no chair you can put it in, and no one is supposed to go in there because that's forbidden. Then that's called band state. So now I have L number of the particles I have find it out. Now then we have an electron comes in. I wanted to plug in the electron in a certain positions, and that will depend on the statistics, and that will tell us why some are metal and some are insulator. Okay, so that depends on how many particles I have, and that depends on the statistics. Why so? Let's go back. Quantum statistics. I said that there are only two particles that exist in nature. One is the boson, one is the fermion, and you can understand have just the two particles. That's enough because these are mutual statistics. In other words, when I have two particles, exchange the two position of those. I got a total wave function which takes the +1 is called bosons. If I take a -1, it's called the fermions. So if someone is outside, two particle exchange, they will see that, well, my phase has changed by +1, -1, and that can tell whether they are boson and fermions. So fermions are actually interesting because it's -1. So that means if I write this two total wave function as a product of the two single particle wave function with n1 and n2 with x1 and x2, to get a minus sign here, when I switch the x1 and x2, you see that I need a minus sign, right? Because if I change the x1 and x2, this part become a second part, and second part become a first part, and I have to get a minus sign to be equivalent to each other. So that means when n1 is equal to n2, that total wave function become a 0 because there's no distinction between them, and that is so-called Pauli exclusion principle that you probably heard of. So fermions should not take, cannot take same state. If there are chairs, no one is allowed to sit on top of each other. If you are fermions, bosons, they do. So they take a different state, and that means an electron has a spin of half. So spin half will allow you to have a spin up and down. So because of that, there are factor of the two more degree of freedom. So I had an L state. In fact, I have a spin. So there are 2L number of the state, including the spin degree of freedom, that are available for an electron can take. Okay. And what nature tells us that the electron comes in, want to take the lowest energy state. That's the principle of the nature. So you want to take this is energy level. The first one will go to the down, the lowest energy state, and you start to fill them up one by one, one by one. If the temperature is 0, the temperature will allow to excite them, but let's say temperature is 0, then they'll fill it up from the bottom to the, one by one. And then once they fill up a certain level, I use up all of the energy, all of the electrons, sorry, all of the electron. So once the electrons are fill up certain level, you can differentiate between the state, the chairs, which are occupied versus the state that are not occupied by the electrons or particles. And they are differentiating between the two. And that differential between the two is called the Fermi energy, EF. Okay. All right. So now with that, let's see in the real space what it means. Imagine that I have 1 electron per site on average, because it's a quantum, they can fluctuate. But on average, I have 1 electron per site. Then I'm filling up the half of the band because I have L number of the particle while I have a 2L number of the state. I have a 2L chairs, but I have L number of people. I can fill it a half of it. That's a high energy. This is low energy. There will be some line there. I can differentiate between the chairs occupied people, chairs unoccupied people. And that line is called the Fermi energy. Okay, now I put the electric field around this. So this potential was initially equipotential. When I put the electric field, it's a gradient of potential. And that means that this will be tilted. And that's allowed the electron to move from one side to the other side. So if I tilt it, then this will moving along. And in that situation, since each of side, I can put 2 particles, at least with up and down different spins, electrons can propagate from one end to the other end. And that means it's a metal. So that's why it's a metal. The fact that it's a metal is because when you have a metal, that means that it's coming from fermions. Okay, so you don't have a metal in bosons, in fact. Okay, so when the number of the particles are less than the number of allowed state, less than 2L, for example, then that is the less than 2 electron particle on average, then we'll have a metal. On the other hand, if I have a 2L particles, fill up all of them in here, but then you have a forbidden gap here. So there's no particle can move around it. In other words, I have filled them up here. If I want to put a particle onto the other here, I have to pay the energy. And that means this is going to be an insulator. So that's why it's an insulator metals exist in this standard theory. Okay, I hope that was give you a good intro. So some copper like this, copper aluminum, so and those ones, well, aluminum at low temperature superconductor, but let's say copper. Coppers are metals, and like some silicons are semiconductors. So semiconductors like silicon will have this band with a filled up to here, and for the coppers will have filled up the partially filling up first band, for example. Okay, so in this picture, what we have ignored is electron-electron interactions. Okay, so I have 1 electron here, and then I make n electrons of them, and I just fill them up by the statistics of the fermions. So I didn't do anything else. But what is really happens in real material is that there are electron-electron interactions because electrons are negatively charged, and therefore there is a Coulomb repulsion between them, and that was ignored in that picture. So when I say correlate quantum material is the one that has this electron-electron interaction, and there are 2 categories. One is weakly correlated, and the other is strongly correlated. So weakly correlated is the what we will go with the standard theory, the 2. So correlate material, but they are weakly correlated. That means is that this interaction here is going to be smaller than this Hamiltonian here. So each of Hamiltonian is the unit of energy, right? So this involves some unit of energy, and this involves energy. This energy scale is much bigger than this energy scale. We'll call that weakly correlated. Backwards, we'll call that strongly correlated. Okay, so for the standard theory 2, let's begin again back to the partially filled band. I tell that I have n electron occupies L state among the 2L state. In other words, L is equal to n. Then you'd expect, okay, think about the spin. This is a metal. N electron with a random spins will be up and down. There's no reason spins are aligned, right? So this particle that occupies this below the Fermi energy will have a random position of the random direction of the spin. And that means if I average over the all of the spin, this will be a 0. And that's the magnetism. There's no magnetism. So when you see the magnets are physics of quantum because it's coming from the spins, and spin, there's no analog of the classical physics. So these are coming from the mainly magnetic moment of the or spin of the electron. And in general, they'll be randomly oriented. So we have paramagnet, so-called, something like this. That's not a magnet, like lots of them are not magnet. On the other hand, some are magnets, like irons. So you put the irons and iron oxide, and some of those can be a ferromagnet, meaning all of them align to each other. So that means that they are talking to each other. Like I say, well, I'm up, veer up and you have to communicate. There is an information carried between the spins while these are still moving around. So this is when S is finite, these are called ferromagnet. And the question is, why some are ferromagnet? So here's a picture. I begin with fermions, where fermions there are billions or quintillion of the electrons. Of course, we have ignored the nucleus. Nucleus sitting in making a solid, and they provide a positive charge. So that total solid is neutral, charge neutral, but they are not in this picture. But there are electrons are moving around, and I said those electrons are non-interacting, which called the Fermi gas. As I increase the electron-electron interaction, those Fermi gas become a Fermi liquid. In other words, gas is more it's like a more kinetic energy, but they become more like a liquid-like. But there is a adiabatic connection. In other words, gas to Fermi liquid are diabatically connected. So this weakly correlated ones can be still described by the non-interacting picture that we just learned. Okay. But as I increase more and more electron-electron interaction, there's a two different are going to be occur, like a ferromagnet occurs after paramagnet. So there has to be a transition between the two, because one of them has this average spin moment being a zero, but the other has the average spin moment being finite. So these two has to go through the phase transition, so-called. So here is a phase transition that separate between two different phase of matter. Okay, and this usually involves the temperature. So there is a so-called critical temperature below which this ferromagnet going to occur. Okay, and well, that's the way to differentiate the different phases of matter. So when you say phase are different, for example, Fermi gas to Fermi liquid, even I include some electron-electron interaction, these are adiabatically connected without going through the phase transition. I can still describe this physics by the non-interacting pictures. So that's why weakly correlated ones or non-interacting picture that I described, the standard theory one, is so powerful because the band theory will describe a lot of material that exists in nature. Okay, or some of this, including the semiconductor, the silicon. Okay, so these phases are different because they have different magnetization, and we call this magnetization as order parameter. Okay, so classification of the different phase, in other words, different phase of matter are distinguished by the so-called broken symmetry and the associated order parameter. So this is a standard theory too. So when I have ferromagnet, for example, we say broken symmetry is a spin rotation because spins are aligned a certain direction. They chose a particular direction instead of having some random direction and make average being a zero. They are all aligned in a certain direction, which are set by some kind of electron-electron interaction. And the order parameter in this case will be a magnetization that we are measuring in the lab. And the extensions around these are called magnons, which I'll come back, coming in later. And the solid is also, solid differ from the liquid. Like, you know that the water, water freezes to the ice, and that is a phase transition. You probably have heard in high schools, right? So gas, liquid, and solid, there is a phase transition between the solid and ice to water. And the difference between them two, the broken symmetry is a translational symmetry, because liquid, you can find the water molecule every distance you're moving because every density is uniform. But solid, because they are solid, is discrete. When I move by arbitrary distance, you can't find the water molecule because there are nothing there. And you have to move a certain distance to find the water molecule. And we call that translational symmetry is broken, left with only a discrete translational symmetry. And in that case, the order parameter will be a density modulation. So you're finding those water, ice are certain patterns, where solid has a certain atoms periodically arrayed. And you can measure those density of the atoms by doing on X-ray scattering and so on. And then the extensions around those solid is called the phonons, which is nothing but vibration of those atoms. And you can quantize them, and that's called the phonons. And there are superconductors, which I'll just skip it. Now let's move to the third one, the beyond the standard theory. Okay. So I said, what time is it, by the way? Because that time I've been watching, but it's always the same. So about 5 minutes. Okay, that's wonderful. Good. So the quantum particle beyond the standard theory, as I said, different phase of matter distinguished by the broken symmetry. Okay, so when you have a measured quantity and you take the sample and then go in your lab and measure it, and then you measure it, X-ray sketching show you some nice spots, while you got some line of spots and line of the instead of spots and lines and so on. You can differentiate them between, oh, that's a solid, that's a liquid crystal, and things like that. Okay, but in some situation, this is where our research begins. Different phase of matter is not distinguished by the broken symmetry. Neither standard theory 1 nor the standard theory does work in this case. So here's the following. So both are paramagnetic insulator, but they can be different phase. So I have this one here, T equals 0, and some quantum parameter here that can be pressure or magnetic field, except the temperature, because temperature is not a quantum parameter, okay? So if you put those pressure, like put the magnetic field in a certain sample, and I'll see a phase transition, meaning that specific heat or something is changing, but I'm not finding any other parameter. So in these two transitions, in fact, the way we can differentiate is the topology of the wave function. So one called topologically trivial and the other called topologically non-trivial. Unfortunately, I don't have much time to go through all the topology, but let me tell you little one thing, which is that imagine, let's go back to the n electron occupies the L state among the two L state. It's a partially filled. This is supposed to be a metal according to the band theory that we discussed, standard theory 1. But what we found is that the material actually is not a metal, it's an insulator. And that means the band theory fails. And often these insulators have a magnetic order, but not always. So let's think about this insulator, and that is called multi-insulator. So this is not a, it is like a partially filled. Band theory tells us it's a metal, but it is not a metal, but it's an insulator. It's called multi-insulator. And they have become a multi-insulator because electron-electron interaction is just so strong. Remember that the one that we ignored or weakly treated was a standard theory 1 and 2. But once the electron-electron interaction is very large, we can use neither of them because this interaction is bigger than the part that we discussed. So in that situation, you can go back to the real space picture. In other words, I have 1 electron per site because it's a partially half filled. Remember, that's 1 electron per site is half filled because you have two state per site allowed. Okay. So I have 1 electron per site here. And if I put them both sides here, I have to pay the energy of the U, which is called Hubbard interaction. And that is a few electron volt. It's very large. Okay, so that means that no electron can propagate because I have to move some particle from one side here, put them 2 here, and then have to put 2 all along the one end to the other end. So it becomes an insulator. But on the other hand, they can do a virtual process, meaning that they can hop from the next side and come back to original site. And that is this situation. Take these 2 sides here and take 2 particles here with a spin up and downs. And I can move 1 electron to the other side. They have to be opposite to each other. Otherwise, Pauli exclusion say that you can put the 2 particles with the same state. But here is a different state because I have 1 spin up and the other spin is a down. And I have to pay the energy of U, but I can release back if I put it the other one here. But I have exchanged up and down particles, up and down spins. So that means this is called exchange interactions. And it's a 4t square over U, which is once some of you have done a perturbation theory, you can easily get this. And that means the spins interact. Okay, this is an insulator, meaning charge cannot propagate. Electron charge cannot propagate. Electron spin is the one they can talk to each other. My electrons, my spin, I cannot move along here. Okay, it's like a traffic jams. Cars cannot move and car carry the charge, but well, drivers can talk each other. There is some extent there, so we can, you can communicate information through the spin. So that's the spin interactions. So in this multi-insulator, spins talk to each other. And the most often, they talk to this so-called Heisenberg interaction that I just draw. The one that I just draw, then I just write down, is a particular form of the interaction here, and that's most often happens. It's very likely this is happening. Okay? So that means that these spins will be ordered, and I can excite them by put a light. For example, I shine a light, and then this ordered state will pattern some particular patterns. It's like you have a water, drop the stone, you have a ripples generated. Those are some collective motion of water molecule. The situation here is like a quantum rather than classical. So in this situation, these excitations are called magnons. And it's a quantizing those excitations, and they are bosons. They are not different from the fermion and boson. So we haven't found anything different from the fermion and bosons, but we have learned over the years that once these spins are interacting some particular way or some peculiar way, then in that situation, spins are not going to align, and they are disordered. And not only disordered, they have very interesting physics, and this is called quantum spin leakage. So this interaction is very peculiar. Instead of having a dot product of each of the same direction, depending on the direction of the ruthenium, like this direction, I'm talking with a certain type of interaction. That direction, I'm talking to other interaction. That direction, I'm talking to other interaction. I'm totally frustrated. I don't know where to point because that fellow pointed up, no, point X and point Z, and so on. So these are frustrated. And in that situations, excitations appears are called Majorana fermions and vortex. So some of you probably interested in high energy physics and so on, neutrinos and so on, have heard of Majorana fermions. Majorana fermions are its own antiparticles. They don't carry the charge, they don't carry the spin, but they carry the heat. So if it exists, how do we know? But they carry the heat, so I know how to detect them. That's how will come later. But I said something fancy here, but they are not just the fancy mathematical word or fancy in the sky. You can find this material in the lab. That's the whole point of the research. So how to design a material where the Majorana fermion exists? Okay, so one thing is that, so over the years, we've learned that, oh, we need a honeycomb multi-insulator, electron-electron interaction, very strong. And if I have a transition metal with a d electron, that's possible. And how do I generate the interaction that is pointing this direction, that direction different? Well, I have to use the so-called spin-off coupling. Some of you will learn this spin-off coupling, some third year quantum. In fact, what means is that, electrons are moving around. And when you're moving around, we say angular momentum. Charged particle moving around, it's like a current. The current will generate a magnetic field, and that magnetic field will couple to the spin, its own spin. So that's called magnetic field generated by the angular motion of the electron, because electron is charged. Okay? Because it's like current, magnetic field, and they'll couple to its own spin is called spin-off coupling, and the wave function changes something like this. Blue is a spin down and up, red is spin up. You mix them around, and that's how you can get them. And that's where we propose, actually it was a University of Toronto group, including myself and my colleague, has proposed that this particular compound is going to be a best candidate where you can find this interesting Majorana fermion. And people have come up with the idea that how you can detect it. As I said, they carry the heat. So that means if I put the temperature gradient along this direction, Majorana fermion is going to move along the transverse to the temperature gradient that I added. And this Majoranas is going to carry the heat. Therefore, even though temperature gradient is along this direction that is added externally, the Majorana, which are moving along the transverse, will generate temperature change along one end to the other end. So that's so-called thermal Hall. Okay, and this one has to be quantized because it's carried by something peculiar object, and that is in fact measured in a lab in Japan, and they do see in fact this kappa xy over t is the thermal Hall. And they do see these quantized values in a certain temperature and a certain magnetic field. This is a setup, okay? I don't have time to go through it, but you can see that these are external field, and the gradient of temperature according transfers to the external temperature gradient, and the ratio is called thermal Hall. Okay, so I have answered two questions. First one is standard theory, and second one is that new emergent quantum particle different from boson and fermion. Yes, they exist, at least in the strongly interacting models. And how you go from model to a real material is a big step here, but I just want to convince you that they may live in the strongly correlated quantum materials. Okay, so with that, thank you for your attention.
Yep. Thank you, Professor. Quantum materials is really cool and fundamental. So that was very insightful. We do have time for some brief Q&A session. Does anybody have any questions?
Thanks again for the talk. Do you have, are there any candidate applications for these quantum materials like quantum spin liquids and Mott insulators?
I'm sorry?
Are there any potential applications of where we could use Mott insulators?
Oh,
or
yeah,
quantum
yes,
spin
yes.
liquids?
I actually have forgotten to link to the first questions. That's very nice. So the reason that we are excited about it is actually back to this question here. Recall that I said, okay, what would be a building block for a quantum computer hardware? So quantum computers, where people have been talking about, I said that, you know, the one that at the moment, the one people use is a superconductor in a Google, for example, is aluminum with the Cooper pairs are going in and out, and that's what you use. Open, all of those are decoherence, like a coupling with the environment. You can easily break the quantum state. The one that we are discussing is those Majoranas, or those are entangled, we call that entangled because they are coming out of everyone's. It's not like a single particle. They are not annihilated locally. It's not like someone coming in, take me out of here. That is not going to happen with those type of particles because they are appearing as all of us. So this is called the long-range entangled particles. So they are free from the quantum decoherence. And that's good for a quantum computer, for example. So this is one of the quantum code or quantum memory protected from the decoherence. And people have been working on so-called topological quantum computations. Yeah, so people are looking for this because of application-wise, that's the one thing. Yeah.
Any more questions?
Hi. For the distinction between paramagnetic and ferromagnetic materials and the temperature at which the phase transition between them occurs for a specific material, what are the intrinsic factors that affect the sort of the critical temperature at which this phase transition occurs, and why is it not constant across the order parameters values? That's my question. There was the graph that you showed for it, I believe.
Okay, so I think if I understand you, although I wasn't able to hear you well, but I think you are saying this part,
exactly,
asking why the transition is curving down here.
Yes, and what are the factors that affect it for different relevant quantum materials?
Sorry?
What are the factors that cause it to vary between different...
Oh, yeah. Yes, that's a very good question. So the reason that I put it this way is because of entropy. So at a zero temperature, this transition is determined by internal energy. But at a finite temperature, we are dealing with a free energy. It's E minus Ts. So the paramagnet here, because they are randomly oriented, they have more entropy. They lowers the free energy. So they invaded this area here and occupies a better space because they have a better entropy compared to this ferromagnet. So that's why this line is drawn that way. Very good question. Yeah, it's very important because even a quantum spin liquid that appears here, sometimes a lot of material, even including the ruthenium trichloride that I discussed, they actually have a magnetic order at a low temperature. But quantum spin liquid has more entropy. So here is a magnetically ordered. If I increase the temperature, I can go into the quantum spin, in a sense that I'm a little cheating. So quantum spin liquid here is not that well defined at finite temperature, but they have this fingerprint of those features, which you can find above the magnetically ordered state, and precisely because the entropy is higher here. Yeah.
Yeah. Thank you, Professor. Could we also one more time give the thank you to Professor Key for the quantum materials talk?
Thank you.